are discussing on the fields and in particular the finite fields. So, we have read the how fields are formed, that means over the commutative ring or the integral domain, how multiplicative inverse is added, if exist then it becomes a field. And we have seen the example that when we take the modulo p, where p is a prime, that modulo p addition and multiplication over zp, how it has formed a field. Normally these if we consider that it is over p, we call this is a Galois field, we call that it is called GFP, that is Galois field. And so, this is GFP, that Galois field of P. If P equal to 2, then normally this becomes GF2, and or what P to the power n, mainly we will be considering some field where GF2 to the power n. So, for GF2 this will be it will be of 2 elements only. So, it will be only 2 0 and 1, 2 elements, and these are 2 elements. So, if I take modulo 2 addition, it is 0 0 plus 0 0 1, 0 plus 1 is 1, and then 1 plus 0 1, and 1 plus 1, this becomes 0. So, it is nothing but our XOR, the modulo 2 addition. This is our modulo 2 addition. Now, similarly, I can write the modulo 2 multiplication 0 0, this is 1. So, this is my modulo 2 multiplication. Okay. Now, before pursuing our discussion on fields and particular prime field, we must read something called the polynomial arithmetic. So, because mainly we will be seeing that how this polynomial operations or the over the field of polynomials, this can become a field. So, first we see the polynomial arithmetic. Now, here actually this polynomial arithmetic, this any polynomial is taken as a variable. Now, mainly here we will be reading the 3 things. One is normal polynomial arithmetic, or we call the ordinary arithmetic on polynomial, ordinary polynomial arithmetic using our basic algebra, and the operations concerned are mainly operations are our ordinary addition, subtraction, multiplication and division. These are the operations we will be seeing. Then we will see the polynomial arithmetic in which the coefficients are the elements of some field. So, now we will see the polynomial arithmetic where the coefficients are the elements of some field. And just now the example or the last lecture we have read the modulo p, then the operations that we will be taking, that will be the modulo operations, that means modulo addition and multiplication. And we can see that the coefficients, if it is modulo operation on modulo p or modulo p, then the coefficients can be Zp, that will be seen. Then another thing, we will read the now polynomial, again polynomial arithmetic. And define polynomial arithmetic, it is defined that the operations are some modulo or modular polynomial arithmetic, better I write, because the operations are on modulo mx. So, I write modular polynomial arithmetic. This is modular polynomial arithmetic on the coefficients are defined on modulo mx. Where mx is a polynomial. Okay. And finally, we will show that with this procedure, that even some field which is not, when we are taking that it is not a field, if we consider that our normal modulo n operation, but using the polynomial arithmetic, particularly modular polynomial arithmetic, this becomes a field, and that is of interest in real life applications. So, first we see the ordinary polynomial arithmetic, the number 1 is ordinary polynomial arithmetic. As the arithmetic here will be only on ordinary multiplication, addition, subtraction, multiplication, division. So, first we consider the our addition, subtraction and multiplication, division we will be seeing later. So, first thing is, first we define a polynomial. So, a polynomial so, we define a polynomial f(x) is n x to the power n, a n minus 1 x to the power n minus 1, n minus 2 x to the power n minus 2 plus up to a1 x to the power 1 plus a0, it is x to the power 0 is 1. So, I can write in this notation that n equal to 0 or some I equal to 0 to n, I equal to 0 to n ai x to the power I, and we call this is a n degree polynomial. So, this degree of the polynomial is degree is n. Now, if I consider another polynomial g x, so let g x equal to another polynomial of degree m, say I equal to 0 to m and bi x to the power I, that means let g x here degree is m. Now, if I take the addition of fx and gx, that means my addition will be fx plus gx, and here I equal to 0 to n ai x to the power I equal to 0 to m bi x to the power I, and let we have considered n greater than m, that means degree of fx is greater than the degree of gx. So, there will be some more terms from, because from m plus 1 to n that terms will be here. So, the sum will be fx plus gx is I equal to 0 to n f ai x to the power I and I equal to 0 to m bi x to the power I. So, what I can do that for I equal to 0 to m, since n less than n greater than m, so I can write that ai plus bi x to the power I. That means that degree wise the coefficients were added. I have some more terms. In the first term, that I equal to m plus 1 to n ai x to the power I. So, the addition is defined like that. Similarly, I can define it is to same as that of my subtraction. So, if it is my subtraction, it is fx minus gx, and I can write this is I equal to 0 to n ai x to the power I minus I equal to 0 to m bi x to the power I, n greater than m, and instead of plus only I have minus, because I equal to 0 to m ai minus bi x to the power I plus as usual this m plus 1 to n, this term will be ai x to the power I. This is my subtraction. Now, is multiplication. If I take the multiplication, the f(x) into g(x), and this will be simply the I equal to 0 to n a I x to the power I into I equal to 0 to m b I x to the power I, and if I do the multiplication, the result will be I equal to 0 to m plus n, and this will be the a I b j, those terms, all the terms will be there. I write c I x to the power I, where I can write where c I is a I or okay, all the terms if I write, it will be a 0 b m plus n. I should write a 0 b k, a 1 b k minus 1 plus a 2 b k minus 2 plus a k minus 1 b k plus a k b 0. So, I can take all these terms, and here actually k I have given. So, it should be k only, okay. It should be k. So, if I take some example, if I take one example, say my f(x) is x cube plus 2x square plus 1, and g(x) is x square plus 3x plus 2. Okay. Now, what will be my f(x) plus g(x)? See, f(x) plus g(x), I can write, if I consider all the terms, that x to the power 3 plus 2x square plus, I can take, since it does not have any x to the power 1 term. So, I write 0 into x plus 1, and g(x) if I add. So, g(x) does not have any x to the power 3 term. So, I coefficient should be 0, then x square, then 3x, then 2. So, if I add, I will be getting x cube, then 3x square plus 3x plus 3. So, the way we have done that, 0 to m, so it is up to 2, only the coefficients will be added. So, 2x square, it has 1x square, so 3x square, it does not have any x term. So, 0 plus 3 3, 1 plus 2 3, and the m plus 1 to n, that means only 1, it is left is cube. Similarly, I can do here now directly, I can write f(x) minus g(x), f(x) minus g(x), since there is no cube degree 3 term. So, x cube minus x square, because 2 minus 1, x square, then minus 3x, because it does not have any 0x minus 3x, plus 1 minus 2. So, it is minus 1. So, f(x) minus g(x) is that. Now, if it is f(x) into gx, that multiply, that ordinary multiplication we are doing, and the coefficients are we are taking. So, this will be x cube plus 2x square plus 1, and we take x square plus 3x plus 2. So, it will be, if I take m plus n, if we remember the way we have written, so it will be x to the power 5 plus 3x cube. The term will be the a0 bk. So, here x cube 3x 4 and 2x 4. So, I can write 3 x to the power 4 plus 2x to the power 4 plus x cube term, that 2x cube then 2 into 3 6x cube plus that 2x4 2x cube, then x square term 2 into 2 plus 4x square 4x square plus 1 into x square plus, now there is no other term here. So, only 3x plus 2. So, I have considered all the thing, then it will be x to the power 5 plus 5x to the power 4 plus 8x cube plus 5x square plus 3x plus 2. So, we get the result here. Now, here the whenever we are considering a polynomial, say fx, say fx equal to I am taking 3x square or 3x cube plus 2x square plus x plus 1, like that. See, here the coefficients are 3, 2, 1, 1. Here it is not there, means it is actually it is 1. Okay. So, now my coefficients are, here coefficients we are taking, it is 3, 2, 1, 1. That means, as if these are integer coefficients we are taking, positive integers or integer coefficients we are taking. Now, so we have defined multiplication, addition, subtraction, multiplication. Now, what about division? What about my division? Because if we remember that our modulo 7, see, if I, because if I want the division, we consider division, then I need some inverse. That means, I can write that a by b. So, actually I can write this is a into b inverse, if it is ordinary multiplication and division. Now, the main point is, or issue is here, whether b inverse exists or not, because just now the from the definition of field we have seen, and we have seen some examples that this multiplicative inverse may not exist. So, here that whether the main issue is whether b inverse exists or not, b inverse exists or not. Say I consider 5 by 3, I consider 5 by 3. So, my 5 is 5 and 3 are integers. Okay. So, if my set is the integer set, then I know that I cannot get this integer as the 5 by 3 1, but because I know this 5 by 3 is 1, the 1 into 3 plus 2. So, that means here I get that remainder quotient 1 and remainder 2, okay. Quotient 1 and remainder 2. So, if my coefficient sets are integer, then actually they are not forming a field, they are not in field, they are forming a field. That means coefficients, if the coefficients are in the set of integers, because if it is an integer, that multiplicative inverse does not exist. So, it is not a field. But if the coefficients are real or complex number, if the coefficients are real number or say rational number or complex number, then they form a, right here in this case I see the real numbers, then they form a field. Now, if I take 5 by 3, now the operation we have seen, say modulo 7, if the multiplication is modulo 7, that is multiplication modulo 7 is modulo 7 multiplication on Z7, then we know that 3 has some inverse, then the element 3 belongs to Z7 has an inverse which is 5. Because 3 into 5 modulo 7 is 1, multiplicative identity. This is multiplicative identity. So, this is, I know that 3 has inverse. So, now if I do the 5 by 3 under modulo 7 operation, then I can write this is 5 into 3 inverse modulo 7, and that is 5 into 5 modulo 7 and is 25 modulo 7 is 4. So, the result exists, and since 4 belongs to Z7. So, this forms a field. So, if I take the coefficients and we take the, instead of normal coefficients in ZP. So, now what is the conclusion? If the coefficients we are taking, in some modulo n, that means set is in, coefficient set are in Zn. Here the examples, then it forms a field. Why we are doing that thing? Because if inverse exists, then we can we can do the division, then it forms a field, and if it is field then inverse exists and then division is possible. Say field. Okay. Now that means what? If it is a polynomial, that means my fx, say fx is, I take a very simple example with 5x cube, and say my gx is 3x. So division, now if I consider division, I can do fx by gx, fx divided by gx, and that is equal to 5x cube divided by 3x, and this is 5 by 3, x cube by x is x square, and ordinary division I cannot get, but if the coefficient is in modulo 7, then just now we have seen that it is 4x square, because if the coefficients because 3 inverse equal to 5, just now we have seen coefficients in Z7, because 5 and 3 or 5, 3 all belongs to Z7, because 0 to 6. So, then I can do then division is possible. So, conclusion is then division is possible. That means multiplicative inverse exists, and multiplicative inverse exists means the coefficient forms a field. Division is possible if multiplicative inverse exists. Multiplicative inverse exists, and multiplicative inverse exists means, and that means that is the coefficients form a field. That means the coefficients form a field. So, why field is very important? Because then only I can do the division also. I can do all the division, etc. So, now we will see that if I consider the polynomial thing, then it is actually if we consider polynomials, if we consider the polynomial, because we are discussing on polynomial arithmetic, polynomial whose coefficients are in ZP, then it is called a prime polynomial. Then it is called a prime polynomial. And some more definition on polynomial is very important, and we will be discussing on that. One is that called the irreducible polynomial and reducible polynomial. So, irreducible polynomial that if the polynomial has no factor, polynomial has no factor, then if a polynomial fx has no factor, that means it cannot be represented as a product of two other polynomials. That means it has no factor, product of two or more polynomials. So, it is similar or analogous to the prime number. Okay. So, if a polynomial cannot be represented as product of two or more polynomial, then it is irreducible. Irreducible polynomial, and sometimes we call analogy with irreducible is called the prime. This is called the prime polynomial. So, this is different. This is a this is not prime. Here coefficients are in prime. Consider polynomial whose coefficient is then the coefficients form a field under modulo addition and multiplication. And if the polynomial f(x) has factor, then it is called reducible polynomial. Okay. If f(x) has factors, has factor polynomials. That means factor means it can be represented as a product of some other polynomials. So, what we see that if we started the discussion with three, one the ordinary polynomial arithmetic and then the so mainly we have seen the ordinary polynomial arithmetic and the polynomial arithmetic where the coefficients are the elements of some field. So, we have seen that if the coefficients form a field, then division is possible. So, these two things we have done, and now we will be in our next lecture we will read this, the third one, when the modular polynomial arithmetic, that means the divisor or that can be treated as itself treated as a variable, and we can take the modulo mx type of thing. So, and whether they form a field and what are the application areas of that. So, how finite fields, mainly this polynomial arithmetic, why it is important, that we will be discussing in our next lectures.